We saw in the last video what were the reasons that data-oriented approach was way efficient than the game objects approach. So we saw the first reason, and that was because of the rendering. Now we're gonna see the second reason, which is very interesting. That why data-oriented approach and game objects approach, where the lines of code are very similar. Here also you're looping over an array, an elements of array, and you're changing the data in the elements of array, and the same thing that you're doing the same thing in data oriented approach. But why is there such a big difference in the performance? All right, so we're going to take a look at that. Now, to understand this, you'll have to always keep in mind this. All right, throughout this video you'll have to keep this in mind, that in our game objects approach, here we are looping over an array of transforms, okay, and we are writing data to that. Here, but in our data oriented approach, we are looping over an array of vector 3 and we are writing data to that. All right, so this is probably the only main difference between these two approaches, that here we are looping over an array of vectors and here you are looping over an array of transforms. And we are writing data over it. We are not just reading, but we are writing. Now, to understand this, we'll have to understand how basically we'll have to understand a concept called heap memory. So this is the heap memory. All right. What this is a chunk of heap memory which is called heap for some reason. We'll get to why it's called heap, which is allocated to your game. And what you see here is are all the memory addresses and or you can say memory spaces. We'll get to addresses, but let's say these are just memory block of memory is allocated to your program. And what happens in heap is, whenever you create an object, it is not stored continuously like the diagram shows, right? It's not. So when you create a new object, it's not assured that the last object was given this space. And when you create a new object, it's not assured that the next object will be given this space. It can be anywhere in the memory. So that's the thing about heap, that all the objects of your classes are scattered across the memory. All right. So all these objects are scattered across the heap memory, and in just random fashion. And each object has a memory address to it, as you can see. So what I also forgot to mention is that these objects which are scattered across the memory can be of the same type. All right. So even when they are of the same type, it's not assured that they'll be allocated memory address sequentially. They are still scattered across the memory. So there's no order to this. In heap, if you're creating an object of a class, there's no order to it. It will be scattered. All your data will be scattered across the memory. Alright, so the next concept that we're going to talk about to understand this is of reference types and value types. So reference types are basically objects of your classes. Whenever you have a class, whether it's a unity class like GameObject or transform, which is also a class, when you create an object of this, that's called a reference type. And the reason why this is called a reference type is because when this object will take some memory, let's say it took this space, it's occupying this. That's it. So why it's called reference type is, when you're storing this in a variable inside your script, and then when you're changing it, you're not actually changing the data directly. Actually what you're doing is, that variable holds an address. So that variable will hold this value, 503. So that variable will hold this value, which is the address to the object, or to the address of a memory location. And whenever you're manipulating any values in that, it is through a pointer. So that pointer, the concept of pointer is little different. It's not in C#, but it's in C++ and some of these languages. But so basically reference type means that you're storing the address of the object, and whenever you're changing the value, it is not directly changing the value over there. What it's doing is, it's using the address to access the memory location, and then it's changing the value. So that's why it's called reference type, because it's a reference that address is a reference to the memory location, but it's not the actual memory location. It's not the actual data which is at the memory location. It's just the address. So what happens is, this is your compiler, right? And you have written some code to change the value over here. What your compiler will do is, it will access the memory location 503, and then you will get your data, right? So this is your data over here. So it's a sort of a two-step process. The compiler goes to the memory address, then it goes to D, and that's the reason why you're able to throw references around in your script, right? And not worry about anything. So that's reference type. What reference type means is you're not directly changing the value, but you're storing the address to that memory location, and the compiler accesses that memory location through the address, and then it changes the value. Now the value types, as the name suggests, and it's contrary to reference type. What a value type is basically all the primitive types, right? Like integer, float, double, all these are value types. Also objects of structure are value types. Alright, and what it means is, you're not actually storing the memory address anymore. What you're storing is the actual data at that memory address. So for a value type, right? For a value type, the compiler, this is a compiler here. You've written some code and you want to change the value, right? So your compiler will directly change the value, the data which is stored at that memory, and it will do this directly. Okay. There's no referencing, there's no address or anything. So it will directly change the data over there. That's reference type and value types. Value types, you're changing the value directly. For reference type, you're not changing the value directly. You're accessing, what you're storing is the address to that value, right? And the compiler accesses that address memory location through the address, and then it changes the value. So now we're gonna talk about something completely different. We're gonna talk about cache, and we're gonna talk about memory, RAM, and all that, right? So the heap memory is stored in RAM, right? All the memory of running programs are stored in the RAM, which is over here. All right. So this is your CPU. The cache memory is a type of memory similar to RAM but very different. All right, similar to RAM but very different. So you have different type of memories. Cache is a type of memory, and then random access memory, which is RAM, is another type of memory, and then you have other SSD, which is more like a storage. The terminology used for SSD is a storage. So you have these memories. Now we're going to talk about just two memories, which is RAM and cache. So your cache is inside the CPU. Okay, you can't see it, it's inside within the CPU. And your RAM is a different chip. You know this, right? The RAM is a completely different chip which is outside your CPU, and there's a bus, or there are tracks, copper tracks going from CPU to the RAM. Obviously, because you want data from the RAM, the CPU needs to access data from the RAM. It needs some connection. So that's why there are these tracks, which is called bus in computer engineering. So there's a bus that connects CPU and the RAM together. So because cache is directly inside your CPU, cache is very fast. For CPU to get some data from cache, it can get it instantly. It's really fast. It's obviously because it's inside the CPU. That's the fastest memory. But because the size of the CPU is so small, the amount of cache is less than RAM, right? That's why you have RAM. Now to get some data from RAM is slower. It is slower than cache. So how the whole thing works is that whenever the OS demands for some data, or whenever your program demands for some data, the CPU will first check for that data inside the cache. All right. This is applicable for everything. This is applicable for software, apps, any platform like mobile, computer, VR, any platform. Wherever there's a CPU and a RAM, this is applicable over there. So whenever a program demands for data, the CPU will first check for that data inside the cache. Alright, and it will check inside the L1 cache. If it's not there, it's going to check inside the L2 cache. If it's not there, it's going to check into L3, and there the L4, and all these levels of cache is going to check sequentially. And for every time when that data is not there in any of these level of caches, right? Whenever a data is not found in cache, it's called a cache miss. Alright, and when it is found, it's called a cache hit. So whenever there is a cache miss, basically when the CPU is not able to find the data in cache, right, that's called cache miss. Whenever it is able to find that the requested data inside cache, that's called a cache hit. So whenever there's a cache miss, then the CPU tries to find it inside the RAM. So this process is applicable to all fields. Okay. First, the CPU checks inside cache. If it's a cache miss, it will check into RAM. If it's a cache hit, it can just quickly process it. So cache hits are very fast. If the CPU can find your data inside cache, that's going to be very fast. So what happens is, whenever so the operating system is smart about this. All right. I'm not sure whether this is the compiler or the operating system, but I feel like this is the responsibility of the operating system. But you can double check this. So one of these programs, operating system or the compiler, they're very smart. What they'll do is they're going to store the data which they think is frequently accessed or is important. The data which is frequently demanded or the data which is important, that it's going to store into the cache. Right? Because if it's frequently demanded, you don't have to check the RAM. You don't have to go all the way to the RAM, which is a very slow operation as compared to cache. Right? So you don't have to. The CPU doesn't have to go all the way to the RAM to get that data. It can quickly get it from the cache and can process and go ahead. Cache operations, cache hits are very fast. If your data is found inside cache, then that's going to give you insane speed. Alright, so one of these, the operating system will store data inside cache, which is requested often, the data which is cache optimized. Alright, and we're gonna look at. So this is another diagram which you can look at to understand the step. Right, so the CPU will first check into cache. If it's not there, then it's going to go into memory. Your main memory is the RAM here, and the reason why you see the arrows bi-direction between the main memory and cache is because if it's not there in the cache, right, and if it's requested from the main memory, then it is first stored into the cache, then it is brought into the CPU for processing. Whenever it is requested, whenever the processing needs to be done, then the CPU acts on it. So the data from the RAM comes to the cache and then it gets processed, but it is not kept into the cache if it's not cache optimized or if it's not needed frequently. Now, what is a cache optimized data? Alright, a cache optimized data is that data which is stored sequentially inside the memory. Alright, if your data can be found inside a chunk of memory contiguously, then that is going to directly be stored into cache. And if your data is all scattered into heap, that's not going to be stored. Some of these objects will be stored in cache, but some may not be. So then it has to jump back and forth to finish just one operation. Right? The CPU will have to jump back and forth from RAM to cache to RAM to process, because some data is found in cache and some is not. So this is a very big overhead. If half of the data is in cache and half of the data is not in cache, is in RAM, or if the entire data, if a chunk of data is which is needed for one frame, if a chunk of data, big chunk of data which is needed for one frame, if all that data is in RAM, then it's going to take that's a big overhead. That's going to take a very good amount of time, and that's why. So if you take a look at this, right, now let's see what's happening here. So in Unity, the GameObject class is a reference type because it's a class. Okay, the transform is also a reference type because it's a class. So what I mean by this is the object of these two classes are going to be scattered across the memory. But if you look at a vector 3, that's a value type because it's a struct. Alright, so this is a value type. The vector3 is a value type because it's a struct, and all struct objects are value type. So no matter how you create a game object, whether you create it runtime using instantiate function, or whether you create whether it's already there in the scene, there is going to be an instance of it. Like there is going to be an instance of it on the heap, which is going to be scattered randomly across inside the heap. So same for transform. No matter whether you create it runtime, whether it's an empty game object or what it is, doesn't matter. As long as there's an instance of it, it's going to be stored on heap and it's going to be scattered. It's going to all be scattered. So over here, what we are doing is, in our code, if you look at what we were doing is, we had an array of transforms, and this means that every player, right? Every player, and we were instantiating this runtime, which is irrelevant, okay? Because whether you do it runtime or whether you do it, beforehand, it is still going to be an instance. It is still going to be a value type. It will still be scattered across the memory. So what you're seeing over here is a comparison. It's sort of like a visualization of how it may look when there is an array of transforms on the left side over here, and when there is an array of vector3, which is value type on the right side. Right. So here is your array of transform, and as you can see, even so this is our player array, and even if you do this, right, even if you access the first one, so this is how, even if you access the first element of the array, and then in the next step, even if you access the second element of the array, their addresses are going to be way different. And so the first one is over here, and the second one is all the way here. So you can see the difference in the address, right? 500, and this is all the way here, 510. So it's all scattered across the memory. There's no order to it. Okay, so all these dotted lines are just garbage data or some other data between your transform objects. So there can be anything over here, and you will not be able to make out. And so the memory kind of looks like this, something like this it looks. But for now, we're gonna just stick with these easy to understand values, and let's take a look at our array of array of vector3s. Okay, so this is our array of vector3s. Now, because this is a reference type, this is a value type. That's why it's not scattered across the memory like this, because you know beforehand how much memory this is going to take. That's why it is stored in contiguous manner, one after the other. It is stored, and when you access this, just like over here, when you were accessing this element, you were accessing the memory address to access the data, right? It was a two-step process. You first access the memory address, and then you get the data. In the case of vector3, you don't access any of these. You access the values directly. Only one-step process. So whenever you do m_player 0 for a vector, you're not going to get an address, right? You're not going to get an address, but you're going to get a vector directly, like inside the compiler. So that's the difference between this. So this is cache optimized. This is way cache optimized. Anything which is stored in a contiguous manner, that's very cache optimized, and compiler is going to pick this up first thing, and it's going to store into the cache, and cache hits will be more probable. Over here, cache misses will be more probable, because it can be that half of the data is in RAM, half of the data is in cache, or no data is in the cache, because they are all scattered. So that's why. So that's the second reason why data-oriented approach is more efficient than our GameObject based approach, and that's the main reason why GameObject data-oriented approach outperforms your other GameObject related approaches. So you should try to stay away from, for games that need huge scale, right? Like MMOs, MMORPGs, and games like PUBG, which are open world, and multiplayer and run on a low-end device like a mobile. For such games, and these games scale with time. They add more DLC, they add more content, they add more guns, they add more type of things. They scale with time. For these things, data-oriented approach is the way to go, because this is very cache friendly, and it's just like there will be just less cache misses. There will be more cache hits, and that's going to be very optimized, and there will be less overhead. The CPU time will be really fast. So yeah, that's the concept that I was talking about. That this is the second understanding that I was talking about. So whenever you're just creating objects on the fly, and whenever you're iterating over large set of objects which are of classes, then this is what's happening. There's a lot of cache misses happening, and whenever you're iterating over, so even this matrix 4x4 is actually a structure. So that's why this is also efficient. So whenever you're iterating over value types, that's more cache friendly, and that's why there's less cache miss, and that's why so there's more cache hits, and that's why the CPU time is faster here, because the CPU does not have to access the RAM, because the CPUs are way faster than the speed of the RAM, right? The speed of the RAM is somewhere about 3000 megahertz, 4000 megahertz, but the CPUs are very fast. They are in gigahertz. So the RAM is very slow compared to a CPU, and if you can find it in cache, that's going to be insanely fast. And this is the other thing. I'm not even used dots here. Okay? We're not even talking about ECS and dots and all that. But when we talk about that, that's a whole different ball game. This is just with basic Unity stuff that I've explained you what is data-oriented approach, and only this gives you a lot of performance. But dots and ECS is a different game, and I want to talk about that, but I'll need some time to prepare that content. But yeah, that is soon coming. But I hope all this content helped you deepen your understanding and gave you insight into performance and game development, right? Game development related performance. And I hope you just don't write your functionality. I hope you also think about these things, because as your game scales, these things will come into picture, and these things will become like technical hurdles which you may face. So I hope you're able to overcome them very easily with this, and I hope this has given you some kind of wisdom and some kind of knowledge that's going to help you. So that's it. I'll see you in more upcoming videos like this.